In this video lesson, we're going to look at the Bronsted-Lowry concept of acids and bases. So to work this lesson, you may want to have a copy of this handout, the Bronsted-Lowry concept. The reason why we're now looking at a new concept or a new theory of acids and bases is because what we know now is that reactions of acids and bases don't always involve water. Since the Arrhenius definition of acids and bases revolves around that whole idea that an acid donates the proton to water, whereas a base steals that proton from water, we need to have our new concept. So basically, the Bronsted-Lowry concept focuses on the role of an acid and a base in the reaction, rather than the properties of an acidic or basic aqueous solution. So the Arrhenius definition focused on how they behaved in water, whereas our Bronsted-Lowry concept focuses on how they behave in a reaction together. And so what we know is that an acid, according to the Bronsted-Lowry concept, donates a proton. That proton is basically a hydrogen atom missing an electron. So if you look at this example of HCl plus water makes our hydronium ion plus chlorine, the hydrochloric acid takes this hydrogen and basically donates it to this water, resulting in the H3. So our HCl donates an H plus, a proton. A base, on the other hand, behaves differently. Instead of donating a proton, it accepts that proton. So in this example, looking at NH3, what it ends up doing is stealing a proton from this water, making NH4 plus and hydroxide. So this time, the proton comes from the water to the NH3 to make NH4. So this time the NH3 steals the H plus. We're going to talk about how water plays two different roles, stealing the proton and also donating the proton, in a minute. So something kind of unique about the Bronsted-Lowry concept is that according to this concept, a substance can only be classified as an acid or base for a specific reaction. What that means is that a substance can donate a hydrogen in one reaction, but accept the hydrogen in another reaction. So substances that can be either an acid or a base are called amphiprotic. So our big example here is water in our reactions. In this reaction, water acts like a base because it steals the proton. But in this reaction, water acts like the acid because it donates the proton. Other examples of this is the bicarbonate ion. That's because the bicarbonate can behave like an acid right here, where it takes this proton and it donates it to the hydroxide group to make an HOH, which we really know is H2O. Or it can behave like a base, where it takes this proton from a hydronium ion and creates H2CO3. So as an acid, the bicarbonate donates a proton to OH, and as a base, it can steal a proton to make H2CO3 or carbonic acid. So basically, how a substance behaves, whether or not it's going to be an acid or a base, depends on what it's reacting with. So one of the key points of the Bronsted-Lowry acid-base reaction is that it can only differ, the products must only differ from the reactants by only a single proton. So when our acid loses a proton, it becomes something called a conjugate base. When a base accepts a proton, it becomes a conjugate acid. So a pair of substances that differ only by a proton are called conjugate acid-base pairs. So let's look at an example. So looking at this example, you want to identify what has donated a proton. So looking right here, HCH3O2 is almost the same as CH3O2, except it has lost a proton. So that means that this right here is our acid. And because right here, CH3O2 differs only by the loss of a proton from the acid, it is the conjugate base. The substance that has gained a proton looks like right here, water has gone from H2O to H3O+. So because it has gained a proton, it becomes the base. And over here, H3O+ is the conjugate acid because it only differs from the base by the addition of a proton, by the addition of an H+. So then looking, this and this is a conjugate acid-base pair. And our other conjugate acid-base pair is our water and our hydronium, because they also differ by only a proton. So take a couple minutes and try to classify the conjugate acid-base pairs in these three reactions. So hit pause, and then when you're ready to check your work, hit play. So I've used some short forms here, A for acid, B for base, CB for conjugate base, and CA for conjugate acid. And then if you wanted to check your pairs, so your acid and your conjugate base are a pair, base and your conjugate acid are a pair, acid, conjugate base, base, conjugate acid. And this one, the reactants are switched, so you had to be paying attention. Here's your acid, here is your conjugate base, and here's your base, and here's your conjugate acid. So go ahead and try the practice on the bottom of this handout to get familiar with classifying and recognizing conjugate acid-base pairs. Okay, and we'll see you next time.